Swayam Prabha. Digital India. Educated India.
Hello, my dear students. Welcome to Swayam Prabha, channel number 15. Course title Pharmaceutical Organic Chemistry 2. Lecture title Benzene and its Derivative. Module number 1, lecture number 2. This course, it is as per Pharmacy Council of India, New Delhi, and it is beneficial for second year B Pharma students. Name of course coordinator myself, Dhamok Vikrant Murlidhar, affiliated to Savitribai Phule Pune University. Name of academic expert, Dr. Sunil V. Amrutkar. Project name BTH Swayam Prabha, sponsored by MHRD, New Delhi. So let's begin with an learning outcome of today's lecture. To understand principle and reaction of aromatic electrophilic substitution reactions. To understand mechanism of aromatic electrophilic substitution reaction. So these are the three things which we will learn. So first one is principle, after that general reaction and its mechanism of aromatic electrophilic substitution in the benzene. So let's see the contents of this lecture. Aromatic electrophilic substitution reaction. So the first reaction from it, that is nitration. After that sulfonation. After that halogenation. After that Friedel-Crafts alkylation and its limitation. And lastly Friedel-Crafts acylation and its advantage over Friedel-Crafts alkylation. So limitation of an Friedel-Crafts alkylation will be an advantage of an Friedel-Crafts acylation. Before starting the session, one must understand some basic concept related with the topic. So there are some terms that will encounter in our session, and so student must know that concepts before learning all these things. So the first term that will be an electrophile. So electrophiles, a reagent which can accept an electron pair in reaction, is called an electrophile. The name electrophile means electron loving, and it indicates that it attacks a region of an high electron density, or we can say a negative center in the substrate molecule. So in our case, we will be coming across that electrophile. It has been generated in the first step, and it has been generated with the help of actually Lewis acid or some other reagents similar to it, and which attacks an region of an high electron density. So here high electron density region, it will be and pi system of an aromatic ring. not actually a negative center, but it will be an high electron density substrate where it will electrophile will be attacked. And electrophiles are electron deficient centers, so that is why they are electron loving, and due to which they are accepting an lone pair of an electron in a reaction. And these electrophiles, they are been represented by E plus. So plus sign, it is been indicating that there is a deficiency. So whenever there is a negative, because the sign on an electron, it is a negative. So negative sign indicate that there are some extra electrons in the molecule. But here it's positive. So it means that nucleus, it needs, or the valence shell, it needs one more electron to fulfill it, and 1 plus, it means that it needs only one electron. So it has been indicated by this plus sign, and remaining will be a molecule. So contrast to that, actually nucleophile it will not encounter in our topic, but contrast to that, a student should know what is also a nucleophile. So nucleophile, it will be opposite to an electrophile. So it will donate an electron pair in a reaction is called a nucleophile. So this electrophiles and nucleophiles, these intermediates are been caused with an heterolytic fission. So the lone pair of an electron, it will be shifted towards an nucleophile, and electrophile will be an electron deficient. And it is due to that electrophile and nucleophile is generated in the same species, because there is difference between electronegativity of both the atoms. So one will be electropositive and second one will be an electronegative. So that is why it is generating an nucleophile as well as an electrophile. So in our case, we will need this electrophile. Again, we will come across with a concept that is carbocation, or also they are said to be an carbonium ion. So these are reaction intermediates which are been formed, and in the second step we will come across all the 5 reactions that, in case of an aromatic electrophilic substitution reaction, that carbocation it is formed in the second step. So organic ion which contains positively charged carbon atoms are called carbonium ions or carbocations. So important here too, it is been understand that don't confuse with an electrophiles. So electrophiles, they are been general for any other atom, but whenever it comes to only an carbon, so it is an carbocation. And they are formed by an heterolytic fission. So there are some other reaction intermediates also, like neutral species or free radical. So we will not go too much further, because we are dealing over here only an heterolytic fission. So we will come across that only thing, that is carbocations. And similar thing it happens in case of an heterolytic fission, that one will be an electropositive center and second will be an electronegative center, and it is due to a difference in electronegativity of both the atoms. And one more thing that we need to understand, that is stability of an carbocation increases with an tertiary carbocation. So this concept we will encounter in case of an Friedel-Crafts alkylation, where a rearrangement product it has been formed, and this rearrangement product it is formed due to an stability of an carbocation in the intermediate step. So starting from an methyl, primary, secondary and tertiary. So stability it increases from methyl, primary, secondary and tertiary. So tertiary is most stable, and in case of an Friedel-Crafts alkylation, so we will come across that tertiary carbocation it has been formed from a secondary carbocation, and it is due to instability, and due to which desired product it is not been formed. One more concept that we will come across, that is Lewis acid. So there are three terminologies been discussed by uh, three different ways for an acid. So RNS theory, Lowry-Bronston theory, and third one that is Lewis acid theory. But there are some limitation with RNS theory, and there are some compounds that can be defined only with the help of an Lewis acid concept. An acid is in any substance that can accept a pair of an electron, and it is having an electron deficient center at the center, an electronegative atom attached to it. Like, so these are some reagents that will be utilized for aromatic electrophilic substitution. So they are having an electro deficient center, that is Al, and metal, and it is been surrounded by a non-metal, that is Cl. So combination of this, so it will create an electron deficient center, because these negative atoms or electronegative atoms, they will abstract an electron from this middle atom. So it is an any substance which can accept accept a pair of electron, because these are electron deficient center at the middle, and so it will accept an electron pair. And one more simplest thing, that is substitution reaction. In case of an organic chemistry, there are 4 types of reaction, and substitution is one of them. So a reaction in which atom or group of atom directly attached to a carbon in the substrate molecule is replaced by another atom or group of atom. So here you can see by a reaction. So one molecule, it will be replaced by another molecule of an substrate. And so these kind of an reactions, they are said to be an substitution reaction. So this electrophile which has been coming towards an carbon, so it should be more stronger, that it can remove this hydrogen, or it should have such kind of an intermediate or catalyst, that it can remove an hydrogen from an carbon and replace this by an chlorine. So in presence of an UV light, and now it will form a substituted product. So let's begin with the first point, that is aromatic electrophilic substitution reaction, and why they are said to be an aromatic electrophilic substitution reaction. A reaction in which hydrogen atom of an aromatic ring is replaced by electrophile are called electrophilic aromatic substitution reaction. In organic chemistry, you will find several type of reactions. Like, there are 4 general categories of reactions. The first one category, that is addition, second is elimination, after that third one, that is substitution, and fourth one, that is rearrangement. So out of that, we today are discussing substitution reaction. In case of an addition reaction, something adds. In case of an elimination reaction, something is being eliminated. And in case of an substitution reaction, so something it has been substituted. And in case of an rearrangement reaction, so the internal structure of a compound, it gets rearranged to a stable structure or to form a product. Now here name, it is indicating that substitution, and substitution may be of 2 types. One is nucleophilic and second one is an electrophilic. So in this case, we are seeing only an electrophilic substitution. And at what? So it is at an aromatic compound. So aromatic compound, here we will study only an benzene, as we are dealing with benzene only. So aromatic electrophilic substitution reaction of an benzene we will be studying. The benzene ring with its delocalized pi electron is an electron rich system. So in the last lecture also, we have seen that how it is an delocalized pi electrons. Benzene contains 3 pi electrons, in which 3 pi bonds, in which pi electrons are been delocalized, containing 6 pi electrons. And that is why it is an electron rich system, that it can donate an electron towards an electrophilic species or electron deficient species. It is attacked by electrophile giving substitution product, and this is a general reaction for aromatic electrophilic substitution. So benzene, when it comes in a contact with an electrophile in presence of an Lewis acid as a catalyst, so it will form a product which has been substituted by an electrophile. So the hydrogen atom over here, which here you can see that this hydrogen atom, it has been replaced by an electrophile. So hydrogen atom, it is also having a positive charge, as well as an electrophile is also having a positive charge. But why it has been replaced? Because electrophile, it is having it is a stronger than an hydrogen, that it can replace an electrophile. And Lewis acid acts as a catalyst to promote electrophile at this position, and it forms an electrophilic aromatic substitution product at the last. So the first reaction we will see from this category, it is nitration reaction. So the principle of this reaction is that benzene reacts with a concentrated nitric acid at 323 to 333 Kelvin in presence of concentrated sulfuric acid to form a nitrobenzene. So very simple reaction. So in case a general reaction, benzene, it is reacted with concentrated nitric acid, and after that concentrated sulfuric acid, and it will form a nitrobenzene. So in case of this reaction, sulfuric acid acts as a Lewis acid, or to generate a nitronium ion we require an sulfuric acid. So whenever this reaction it has been carried without an sulfuric acid, so that reaction will not proceed, or it will not form a nitrobenzene, because nitronium ion generation, it requires an sulfuric acid. So nitronium ion, it has been generated by use of an sulfuric acid, and at the last it will also form in water by removing a hydrogen from an benzene and remaining part of a nitric acid. So it will form in water with it. Now we'll see the mechanism of a nitration. So in general, for every electrophilic aromatic substitution reaction, there are 3 steps. So first step is generation of highly reactive electrophile, that is nitronium ion. So here you can see the structure of a nitric acid. So electron rich oxygen on nitric acid, it donates an electron towards an hydrogen. So this arrow, it is called fishword arrow, and it is indicating a transfer of electron towards an hydrogen. As soon as the electrons are being transferred on an hydrogen, so the bond between hydrogen and oxygen, it will break, and this sigma bond, as soon as it break, so it will transfer an electron over an oxygen. Now oxygen will be an electron rich species, and hydrogen, it will be an electron deficient species, because the arrow of an electron, it is indicating that electrons are being transferred on oxygen. So after that, it forms an hydroxide ion on nitrogen, and due to which electron rich oxygen donates an electron towards an electron deficient nitrogen, and due to that, now this water molecule, it has been removed by breaking a bond between nitrogen and oxygen. So the breaking of this nitrogen and oxygen bond, it is due to that electrons from an oxygen, it has been shifted on nitrogen, and now which creates a bond. So now valency, it is beyond 4, so that is why it breaks. So one is forming and next is breaking, and it is a reversible reaction, and now it is generating a nitronium ion plus water. So now in the next step of a nitration, it is attack of an electrophile by aromatic ring. So this nitronium ion is an electrophile, and electron rich center, that is benzene, it is having an pi electron system, out of which pi electron it will react with electron deficient nitrogen, and this arrow, it is indicating that pi electrons, they are attacking an electrophile, and due to which electron deficient nitrogen, the bond between oxygen and nitrogen, it will break and electrons will be transferred over an oxygen, and now it will form a negative charge. So whenever this bond it has been breaking, so at the one end it forms an electron rich center, that is carbon carrying a negative charge, and at the one end it forms an electron deficient center. So it means that unequivalently the bond it has been broken between two carbons, and one becomes electron rich center and another becomes electron deficient center, due to which here you can see an electron deficient center having a positive charge, and this electron rich center, it attacks on nitrogen, and as soon as it attacks the nitrogen and oxygen, the bond will break and electrons will be transferred over an oxygen, and that is why it forms a negative charge, and nitrogen, it will be remaining as an electron deficient as itself, it is having a positive charge on it. And in the third step, it is deprotonation. So deprotonation, it means that hydrogen atom from here, it has been removed, or it donates an electron towards this carbon, and due to which now the benzene ring again gets stabilized and it forms an pi bond once again. So the electrons of an hydrogen, they are been given away, and it is formed due to this sulfuric acid structure. So the oxygen of this acid, which is electron rich species, which abstract an hydrogen atom from a benzene ring, and now this hydrogen, it will donate an electron towards and a carbon, and due to which now a pi bond it has been formed between both the carbons, and now this is our product nitrobenzene, which has been desired. Plus H2SO4. Now we'll come towards an next reaction, that is sulfonation. So name itself indicates that sulfonyl group it has been added. Statement: benzene reacts with sulfur trioxide and fuming sulfuric acid to form benzene sulfonic acid. Structure of benzene: and sulfur trioxide, it reacts with an benzene in presence of an sulfuric acid, fuming one, and it forms an benzene sulfonic acid as an product. Now we'll see the mechanism of an sulfonation. So first step is, as usual for all the electrophilic aromatic substitution reaction, that is generation of an electrophile. Sulfur having 6 valencies, So for generation of an electrophile, the hydrogen atom on sulfuric acid, it will be abstracted by and electron rich species of an oxygen from sulfur trioxide, and due to which the bond between hydrogen and oxygen, it will break and it will transfer electron from hydrogen and oxygen bond towards an oxygen, and now oxygen will have a negative charge while hydrogen will have a positive charge. So after that, triple bond triple bond on oxygen, it has been formed, and now it has been generated an electrophile. So in the next step, attack of an electrophile by an benzene ring. So same thing happens, that pi electron from an benzene ring. So pi electron, it has been shifted towards one carbon, and another it becomes an electron deficient center, and due to which electron rich center, it attacks on electron deficient atom, and now a bond between oxygen and sulfur, it will break, and electrons will be shifted on oxygen. So electrons will be shifted, and now it will form an OH bond. So here again the valency of sulfur, it becomes 6, and benzene ring, now it is an electron having an electron deficient carbon in the middle. Third step, that is deprotonation. So in the first step, which was released by this sulfuric acid having a negative charge on oxygen, now it will abstract an oxygen from an benzene ring. So arrow, it is indicating that electrons are being transferred on an hydrogen, and now hydrogen will break a bond between the carbon and oxygen, and it will donate an electron towards an electron deficient carbon, and due to which again there will be an pi bond formation, and of an sulfonation. Now next reaction we will see, that is halogenation of an benzene. So name itself, again it is indicating that halogens are being reacted with an benzene. So the principle of reaction, benzene reacts with chlorine or bromine in presence of Lewis acid such as aluminium trichloride or ferric chloride to give chlorobenzene or bromobenzene. The structure of benzene, in presence of an chlorine or bromine which reacts with an benzene. So this reaction, it is carried in the presence of an Lewis acid like FeCl3 or aluminium trichloride. So such kind of an reactions, they are being carried with very dry conditions. Usually we see that a round bottom flask, it has been connected with an condenser. So these are the general reaction, that round bottom flask connected with a condenser. But in case whenever we are using Lewis acid such as aluminium trichloride, at that time condition should be very much dry to get an yield of an product, because already we get very less yield with an aluminium trichloride type of an reaction. And for such condition, either a guard column of an calcium chloride, it is being utilized, or balloons of an some gases. Some gases means like inert gases are being utilized to maintain an environment which will be dry. and it forms an chlorobenzene plus HCl. Now we'll see the mechanism of an halogenation. So in the first step, that is activation of an Lewis acid. So bromine are having an equivalent atoms, but due to Lewis acid, it becomes inequivalent when we are conducting such type of a reaction with an equivalent atoms. So it will lead to formation of an free radicals, but due to presence of an Lewis acid, so it will be unequal distribution of an electrons. So this bromine, it will be negatively charged, and this bromine, it will be an positively charged, because the bond, it is breaking between the bromine, so electrons are being shifted towards an bromine, and due to which it becomes an electron rich species, and now it will attack an electron deficient species. So here it is ferrous, which is an electron deficient center. All the Lewis acid contain an electron deficient center, while the Lewis base, they contain electron rich center. So now here you can see that bromine, it is having a delta positive charge partially. After that, in the second step, attack of an electrophile. So electrophile which is been generated in the first step, and benzene ring attacks on an electrophile. Again the pi electrons of an benzene ring, so they will attack on bromine, and the bond between bromine and bromine, it will break, and electrons will be shifted on the bromine. Now it forms an carbocation intermediate. And third step, that will be deprotonation of this carbocatonic structure. And again same will be the thing, that electrons will be shifted from this hydrogen and carbon bond towards an carbon, and it will form an pi bond. And now this is our desired product, that is bromobenzene plus HBr plus FeBr3. After that, next reaction, that is Friedel-Crafts alkylation. So again, name itself, it is indicating that alkyl group, it has been transferred, or it has been substituted on benzene ring. Friedel-Crafts alkylation involves the alkylation of an aromatic ring with an alkyl halide, strong Lewis acid as catalyst. So the general reaction for this Friedel-Crafts alkylation is benzene. It reacts with alkyl halide, and this reaction, it is carried in the presence of an Lewis acid, and now it will form an alkyl benzene. It is called alkylation reaction because alkyl group, it has been substituted on benzene, and hydrogen which is removed, and it forms a bond with X, so that it forms an halogenated product. After that, mechanism of an Friedel-Crafts alkylation. So in the Friedel episode of an electrophile. So electrophile, it has been generated. Alkyl halide reacts with an AlCl3. So again, such kind of a reaction, that AlCl3, it has been utilized. So these reactions are carried out at very dry conditions, because AlCl3, when it has been hydrated or when it comes in a contact with water, it forms an it forms an product which is inactive, and this inactive product leads to an this alkylation reaction. So these reactions are carried out in very dry conditions. All the molecules or all the compounds, they are been dried firstly in a oven or by any another technique, and then only the reaction is further carried out. Even the solvents which are being utilized for such kind of a reaction, they are also dried, with the use of an calcium chloride, or either they are been distilled out to remove a water molecule. As soon as the water it comes in contact with aluminum trichloride, so it will form an hydrated product, and which is inactive, which reduces the yield of an reaction. So this electron rich halogen, it reacts with an electron deficient center, that is Al of an Lewis acid. After that, it will form an partial charge or partial bond with an AlCl3, and now this bond it will break, and a carbon and chlorine bond, as soon as it breaks, now it becomes an electron deficient center. Because so why this happens all the time, that electrons are being carried towards only one atom. So atom which is more electronegativity, that such type of an atom, they will carry an electron with itself, and another carbon it will be an electron deficient. Now it has formed an carbocation, or we can say it has formed an electrophile. So in the second step, attack of an electrophile. So electrophile it will attack. Again the same is the process, that pi electrons from an benzene ring. So this pi electron from an benzene ring, it attacks on electrophile, and due to which the electron deficient center get attached to an carbon, and it forms an aromatic carbocation now. And in the third step, that is deprotonation. So deprotonation means, again similar to the thing, that hydrogen it has been its electrons are been shifted towards an carbon, and it has been carried out away by chlorine. Electron rich chlorine, so it will abstract an hydrogen from here, breaking a bond between carbon and hydrogen, and due to which pi bond again it has been formed between a carbon of an benzene ring, and now we get a desired product, leaving AlCl3 as a catalyst behind, and again also it will form an HCl over here as a byproduct. But there are some limitation with Friedel-Crafts alkylation. So the first thing, that is rearrangement of an carbocation. So benzene, when it has been reacted with an isobutyl chloride in presence of an Lewis acid, the undesired product we are getting, that is tertiary butyl benzene. Actually the desired product it is different, but we are getting tertiary butyl benzene, and it is due to an rearrangement of an carbocation. Carbocation tries to attain an possible stability, and due to which possible stable structure, it creates an different kind of a structure than desired one. So here we can see how actually it forms when it has been reacted with an Lewis acid, that is AlCl3. So chlorine, electron rich species, it will attack on aluminium, electron deficient species of an Lewis acid, and after that there will be a molecular complex, and now chlorine it will depart from this isobutyl group, and due to which there will be shifting of an hydrogen on the adjacent carbon atom. And this is why, because whenever it forms an carbocation over here with such kind of an structure, it will definitely form a carbocation, because chlorine is taking away an electron from this isobutyl structure. So here it has been expected that it forms a primary carbocation. But the sequence of an stability of an carbocation, why it happens that hydrogen it has been replaced on the carbon, it is due to the fact that tertiary carbocations are more stable than secondary and then primary. So here it was forming a primary carbocation, but possibly it can make this tertiary carbocation, and due to which here also you can see that due to which there is difference in an whatever it has been reacted and whatever undesired product we are getting. So it is often tertiary butyl complex which get attached to an benzene, right? And it is due to a tertiary carbocation which gives such kind of a product. Or otherwise, if it is not rearranging, so it might have given this CH2 chain in between, and this CH2 will attach to this benzene ring, but it does not happen in the fact. And now it has formed a tertiary carbocation, and this tertiary carbocation, or we can say an electrophile, it attacks on benzene in the second step, and after that deprotonation it has been carried out in the third step, and we get an desired one product. So the second limitation of an Friedel-Crafts alkylation is that this reaction fails on benzene ring bearing strongly electron withdrawing groups. So whenever there are electron withdrawing groups, at that time this reaction cannot be carried. So this reaction be carried with an benzene, but when it is having an electron withdrawing group, so such kind of reactions cannot be carried out, or it is giving no product. And the groups of such kind, so it has been listed over here. So mostly all the carbonyls like aldehydes, ketones, carboxylic acid, ester, amides. After that sulfonyl cyanides or nitriles or nitro, and after that amino, tertiary amine, and after that CF3 and CCl3. So these are some electron withdrawing groups due to which this reaction is unable to carried out, and there is no product formation in such kind of a reaction. Another limitation of Friedel-Crafts alkylation is that vinyl halide and aryl halide does not give Friedel-Crafts alkylation. And it is due to the fact that when vinyl halide, it reacts with FeBr3, that is Lewis acid, and this one is an alkyl halide having a double bond in between. So electron rich center, that is bromine, it will react with an or it will transfer an electron towards an ferrous, and after that it will form a complex molecule, and this complex molecule they will leave out an or carry away, bromine will carry away an electron from this alkyl group, and it will form a carbocation. So carbocation which has been formed, which has been sp2 hybridized, having a double bond at the center, this carbocation which has been formed, it is very unstable, and due to which there is no formation or there is no alkylation by using a Friedel-Crafts reaction of an benzene with an vinyl halide. Same in case of an aryl halide. Chlorine is electron rich center, it reacts with an Lewis acid and it forms a complex, and as soon as it forms a complex, so this complex will carry an electron with itself, that chlorine will carry away an electron leaving behind an carbocation, but the phenyl carbocation which has been formed, it is too unstable to react, and due to which there is no Friedel-Crafts alkylation in case of an aryl halide also. Now the next reaction, that is Friedel-Crafts acylation. Friedel-Crafts acylation reaction involves the addition of an acyl group to an aromatic ring to form aromatic ketone using Lewis acid as catalyst. So here it's a general reaction that benzene, it reacts with an acyl group. So acyl means having an carbonyl in between. So earlier we have seen halide. So halide, it only contains R and X. Now here acyl, it means that it is containing an carbonyl in between. in presence of an Lewis acid, and it forms an aromatic ketone. So aromatic ketone, because aromatic ring at one side, and one side it has been uh, substituted by an alkyl group. Now we'll see the mechanism of an Friedel-Crafts acylation. First step, that is generation of an electrophile. Electron rich species, that is chlorine from an acyl, so it will attack on AlCl3, and after that it will form a complex, and this complex will break by breaking of an carbonyl carbon and chlorine bond. It forms an electron deficient carbon, that is generating an electrophile. So such kind of an electrophile can be seen that it is shifting an electron from an electron rich oxygen towards an carbon, and it is due to that it is having a lone pair on an oxygen, and due to which it is shifting an electron towards an carbon, and it is said to be an acylium ion. After that, next it is attack of an electrophile on by aromatic ring. So this acylium ion, a pi electron from an benzene, which has been which is due to breaking of an carbon-carbon bond between an aromatic ring, and now electron it has been shifted on an carbon, and after that oxygen it gives an electron, carbon, it gives carbon and oxygen bond, which is triple bond, it gives an electron towards an oxygen, and now it forms this acyl moiety or acyl electrophile. It has been now been attached. And third step, that is deprotonation. So hydrogen, it will liberate an electron towards this carbon atom, and due to which it forms an carbon-carbon double bond, and it is with the help of AlCl4. Electron rich chlorine, it will abstract an hydrogen, leaving an electron towards an electron deficient carbon, and now we get our desired product. So acyl, it is our desired product, acyl benzene, or we can say aromatic ketone. Forming extra product, that is HCl, and Lewis acid as it is, that is AlCl3, being a catalyst. Now we'll see what are the advantages of an actually Friedel-Crafts acylation, and it is an advantageous to Friedel-Crafts alkylation. So in case of an Friedel-Crafts alkylation, we can see that there is rearrangement of an carbocation. But in case of an Friedel-Crafts acylation, there is no rearrangement. So whatever the disadvantage of an Friedel-Crafts alkylation, that can be overcome by Friedel-Crafts acylation. Just we need to increase one more reaction, and after reduction, we will get the same product. So the limitation of Friedel-Crafts alkylation can be overcome by Friedel-Crafts acylation. In case of an Friedel-Crafts alkylation, only alkyl benzene such as methyl ethyl or tertiary alkyl can be prepared from alkyl halides. But with other alkyl halides, it undergoes the rearrangement reaction. So it means that whenever we are taking a straight chain compound, so that straight chain compound, it undergoes an rearrangement, because the tertiary whatever carbocation it has been prepared, tertiary it is one of an most stable, and any molecule will try to attain stable structure, and due to which it undergoes an rearrangement reaction. So it is not possible to prepare a straight chain compound by using Friedel-Crafts alkylation. This limitation of an Friedel-Crafts alkylation can be overcome by Friedel-Crafts acylation and followed by Clemmensen reduction sequence. So we will see a reaction over here. So this is a structure of an benzene. After that, acyl halide, and in the presence of an Lewis acid, so it forms an ketone, aromatic ketone particularly. And after formation of an aromatic ketone, so this is up to this step or second step, we can say this is our desired product as per an Friedel-Crafts acylation. But to overcome this limitation of an Friedel-Crafts alkylation, we need to proceed reaction by one more reaction sequence, that is Clemmensen reduction, by using reagents of an Clemmensen reduction. So further we can proceed the reaction. So now we can get an propylbenzene as an product. So this propylbenzene, this cannot be prepared by Friedel-Crafts alkylation, because whenever we are going for a Friedel-Crafts alkylation, so it forms an rearrangement product, and due to which it forms an isoproduct actually, and this isopropylbenzene is being formed by an Friedel-Crafts alkylation. So earlier also in that limitation we have seen, so we does not get such kind of a chain compound, straight chain compound. By reducing this carbonyl carbon, now we can get a straight chain compound of an propylbenzene. So whatever the elongated chain we can prepare, so that much elongated chain that can be prepared by Friedel-Crafts acylation. So now we'll come to a summary of this session. So we started with an aromatic electrophilic substitution reaction. So aromatic, it means that benzene ring we are considering over here. So electrophile, that is electron deficient species, and substitution reaction means the aromatic CH, or we can say hydrogen of an aromatic ring, it has been substituted by a strong electrophile by use of some reaction conditions such as Lewis acid, and in case of by using some another reagent as well as an heat. So the first reaction we seen in that case, that is benzene, it reacts with an nitric acid in presence of an H2SO4, and it gives an nitrobenzene. So H2SO4 over here, or sulfuric acid over here, it has been required to generate an nitronium ion. So at the first instant, so similar is the step for each and every reaction, that in the first step electrophile it has been generated, and in the second step the attack of an electrophile, it is done by an pi electrons of an benzene ring, and it forms an intermediate carbocation. And after that, again this catalyst which has been utilized, so it will abstract an hydrogen from a benzene ring, and it will form an nitrobenzene. So a three-step mechanism also we have seen in case of a nitrobenzene. After that, we have seen a sulfonation reaction. So in case of an sulfonation reaction, sulfur trioxide, it has been utilized with the fuming H2SO4, and we get an benzene sulfonic acid. So similar way, like there are three steps. So in the first step, electrophile it has been generated, and in second step, the electrophile whatever it has been generated, SO3H over here. So this electrophile, it reacts with an benzene, the pi electrons of an benzene, and we get an benzene sulfonic acid. In third step, or in the third reaction, we have seen reaction of an chlorobenzene by using Lewis acid as an catalyst. So chlorine gas, it has been utilized, and it forms an chlorobenzene. So like similar way, there are three steps. So in the first Lewis acid, it reacts with an chlorine and it generates an electrophile. And in second step, electrophile, it reacts with an chlorine, uh, with an benzene, and one proton, it has been removed from an benzene ring, giving away an electron towards an benzene electron deficient carbon. And this carbocation now forms a stable bond with one more carbon, and it creates an chlorobenzene as a product. After that, we have seen Friedel-Crafts alkylation. So introduction of an alkyl group or substitution of an alkyl group on benzene is said to be Friedel-Crafts alkylation. So in case of that, alkyl halide is required as a substrate and Lewis acid as a catalyst. So in the first step, again similar thing, that it forms an electrophile, and this electrophile, it reacts with an alkyl benzene, with an benzene, and whenever it reacts with an benzene, it forms an carbocation as an intermediate, and this carbocation gets an electron from an proton of an benzene, which has been cleaved with the help of an Lewis acid, and the pi bond which has been again formed, and it forms a stable structure, that is a alkyl benzene. So we have also seen some limitation of an alkyl benzene, that Friedel-Crafts alkylation, that it does not form a straight chain product, and this straight chain product, it is not formed because there is a rearrangement in between, and molecule or alkyl halide, whatever it has been utilized over substrate over here, so it undergoes an rearrangement reaction, and this rearrangement, it is due to an stability of an carbocation. So carbocation tries to attain a stable structure, and it tries to form an from secondary, it tries to form a tertiary carbocation, and due to which, instead of an propyl chain, if we are introducing in case of an alkyl, so instead of that isopropyl, it has been formed and not n-propyl. And there are some other limitation, that whenever it is having an electron withdrawing substituents or electron donating substituent, so at that time there is no reaction, and it is due to instability of an electron cloud in between, and there is no working of this Friedel-Crafts alkylation. And this Friedel-Crafts alkylation, or whenever we are utilizing Lewis acid such as AlCl3, so such type of reactions, they are being carried out at very dry conditions, and in such cases some calcium chloride guard tube or some balloons of an helium, they are being utilized to keep conditions dry. After that, we have seen a reaction within acyl halides, and this acyl halides, it forms an ketone, and these ketones are aromatic ketones because it is in combination with an benzene ring. So in case of this Friedel-Crafts acylation, so because acyl group, it has been substituted, so it is said to be an Friedel-Crafts acylation. And there is advantage of an Friedel-Crafts acylation, that it does not form an rearrangement product. So whatever the disadvantage of an Friedel-Crafts alkylation, so it can be overcome by an acylation. So isopropyl, which has been formed in case of an Friedel-Crafts alkylation, so that can be prepared with an N chain, and straight chain compound or alkyl straight chain compound can be prepared by using this Friedel-Crafts acylation. So it has been followed after that by an Clemmensen reduction. So this carbonyl group, it has to be reduced, and after that it will form a straight chain, or we can say a hydrocarbon chain compound with an aromatic ring. So this was a summary of electrophilic aromatic substitution reaction. Thank you. We have completed module number 1, lecture number 2, and lecture ID M1L2.